Okay, let's get looking at this shortcut method for differentiating, and there's a couple of ways of describing the expressions that we're going to differentiate. I might just call them an expression or a function where x is to a power. You may also hear me refer to it as a polynomial. Now, there's a whole chapter that we do when a little bit later, and we officially define an expression with or a function. For example, a function that has ax to the doesn't matter, ax to the n plus bx to the m plus c mno plus to the p. So all this means is this a, b, c and d, they're just coefficients, numbers that can potentially sit out the front. And we've got x terms, and n is just some power. It could be 1, it could be 4, m could be 3, it could be 2, and I'm just using different letters to indicate. It could be 8 or -5. Okay, so these are the types of functions that we're going to be differentiating now. And just be aware, yes, sometimes, and sometime later, they will be identified as a polynomial. All that means is x is to some power. Okay, let's have a look. So if our f of x is just simply x to the n, so if we had f of x is equal to x to the 4th, then f dash x, which is our notation for the derivative, and you must pay attention to that little dash, is bring the power to the front and subtract 1 from the power. So f dash x in this case is bring the power to the front and subtract 1 from the power, f 4x cubed. Now your understanding is this is the function. This, however, gives me an expression for calculating the gradient at different places or different values of x, so at different locations along the curve. It then goes on to say that if y was a function in x plus or minus a g of x, let me explain what that means. If y, and I could have used y here, is equal to x to the 4th, if y was equal to now 2, so I'm going to say I've got x to the 4th plus 2x cubed. So I'm adding some functions. You know what? We really don't have to differentiate. And we don't have to say really that they're two separate functions, because they could be put together and belong to just one function. We tend to just call that a function in x. And we differentiate them as if they were individual functions, using the rule for as if that was an individual function. The notation this time becomes dy dx, and we bring the power to the front, subtract 1 from the power, and do exactly the same here. 3 to the front, and 3 then times 2 is 6x squared. So that's what that rule is about. Part 3 says if y is a constant, then y dash is naught. let me illustrate that for you. So if y is equal to 2, remember we said it is really 2 times x to the naught. I suppose there is an x term in there, but we don't ever show it because anything raised to the 0 power is 1. But by putting it back in, it enables us to differentiate. So dy dx, oh hang on, I've used another notation now. Another notation is a y dash. Would be, bring the power to the front. Once you've got a 0 out the front, it doesn't matter what you're multiplying anything else by, y dash is 0. And then it says if y is equal to a constant times x, for example, y is equal to minus 3x to the power 5. Where k is a constant, then y dash will also be a constant. Well, I'll take the 5 off. Let me take the 5 off. So remember it's got a power 1. Bring it to the front. It'll be 1 times minus 3 times x to the 1 minus 1. So it's 1 times minus 3 is minus 3. X to the naught is 1, so y dash is just a constant. Now remember, these are differentiation rules for when you've got x to a power. Now, this rule, unfortunately, does not cover the situation where x is in a denominator. So the rule does not apply when x is in the denominator. We will learn another rule. Remember me saying we're going to learn the quotient rule, and that is how we will differentiate when x is in the denominator. However, it is possible in this case to get x out of the denominator. So it just is possible to write this as f of x is equal to x to the minus 2. And when I do that, I won't have any trouble differentiating. I'm going to call it, my notation will be the f dash x. I'll bring the power to the front and subtract 1 from that power. Minus 2 subtract 1 is negative 3. So keep that in mind. If x appears in the denominator, you're going to have to rewrite the function with, and in this case, a negative power. Now that's why we've just revised indices so that you're familiar with how to take x out of a denominator and bring it back to the numerator. The other situation that you also have to be aware of is when x appears under a square root. So they're going to be the two complications. You're going to be given more than just bringing numbers to the front and subtracting 1 from the index. You're going to be given situations where x is in the denominator or x is under a square root. But again, we've just revised indices and we know that it is possible. It's possible to rewrite this f of x as x to a half. Square root is x to a half. That's why we've just revised indices. And now it's in a format such that I can bring the power to the front and subtract 1 from the power, which gives me a half x. Subtract 1 is minus a half. So it's 1 over 2 times 1 over x to the half, positive a half, because that's the definition of a negative index, which is 1 over 2 square root x. Now I'll stop the video there and talk about these examples in the next video.